So now let's proceed with the first presenter, Mr. Mohammed Yousif Zeain from Universiti Teknikal Malaysia Melaka, UTM, presenting optimizing helical antenna gain with artificial intelligence, a paradigm shift for next generation 5G, 6G communication. Please welcome.
Thank you so much. Assalamu alaikum, everybody, and thank you for taking time to join me today. My name is Mohammed Yousif Zeain. I'm a PhD student from University Teknikal Malaysia Melaka and Prof. Zahra Al-Abhas career. So our topic today is how to use AI to enhance the antenna performance. So our title today is optimizing helical antenna gain with artificial intelligence AI, a paradigm shift for next generation 5G, 6G communications. Actually, this is a part of my research. So, can you hear me? Hello? Hello?
Testing. Yes, we can
Uh,
hear you.
okay, thank you. So, helical antenna, one type of antennas. Helical antenna or helix, same meaning actually. So we have two type of helix. One is the helical antenna that built the helical antenna built on the ground plane, which is using wire. So this one called uh, traditional helical antenna. And the feed point will be connecting between the bottom of the helical antenna, as we can see here, the bottom of the helical antenna and the ground plane. For the helical antenna, it is working in two modes. One is the normal mode, another one is actual mode. The geometry and operation, as we can see here, here is the traditional helical antenna using wire. The h here is the height of the helical antenna. D is the diameter. So when we design helical antenna, we have to consider the number of tens. Here, for this antenna, we have three tens. 1, 2, 3. And the S is the spacing between each tens. And here is the ground plane, and the feed point will be connecting between the, as I mentioned earlier, between the bottom of the helical antenna and the ground plane. We move to another type of helical antenna, which is printed helical antenna. The printed helical antenna using it depends on the researcher, or depends on you how you're going to design your printed helical antenna. Here we're using a cylinder, which is considered a substrate A, and here the substrate B. So as we can see here, the red one, which is the strip helical antenna, this one actually is a strip helical antenna, or the copper tape. We use it as a we use it for the printed helical antenna. So here we present antenna or helical antenna with 110. We have to move to the next slide. Is the calculation. We have to use it to design the antenna, and is the number of tens as we mentioned here, 1, 2, 3. This is N, and the S is the spacing between each 10. And continue doing the calculation for the helical antenna, like the actual ratio and the bandwidth. And then design specification. In this presentation, actually, we design a printed helical antenna with circle ground plane, as we can see here. This is a helical antenna with 110. 110. The yellow, as we can see, is the yellow color is the copper. The blue one is substrate B, and here is substrate A. And you can see here in the figure B, the feed line is connecting between the strip helical antenna, the bottom of strip helical antenna, and the ground plane. The first, when we design the helical antenna, we have to design as first 10 or with 110. After that, we can extend to 10s, 10 or 20, depends on you. So the design specification here, as we can see from the table, the total length of the helical antenna, 550. Here we mean the length of the strip helical antenna, the yellow color. But the highest, 123.6 mm, which means the spacing should be 12.36, as you can see here. Times 10, it will be 123.3, 123.6 mm. With the ground plane, 40.18 mm. Actually, it depends on you if you want to design the antenna with circular ground plane or square. We have designed different type of antenna. Maybe I can share with you here. For example, this antenna is a square ground plane. Square ground plane, if you can see here. But here we're using different type of substrate, which is the paper. Okay. And then we go to next step, which is the simulation result. Based on the simulation result using CST software, the proposed helical antenna has a bandwidth of 2.9 gigahertz, which is starting from 4.6 to 7.5 gigahertz. As we can see here from the S parameter, below minus 10 dB, covering the band from 4.6 to 7.5, which means this helical antenna can be used for or covering some of the sub-6 5G frequency band and some of the 6G, starting from 7 to 24 gigahertz. This frequency band, 7 to 24 gigahertz, called the golden band by some researcher, because it's mixed with the millimeter wave frequency band for the 5G. So this why it's called golden band. As we know that the helical antenna provides circular polarization, which means we have to measure the actual ratio. Actual ratio should be minus 3 dB. Based on the simulation results, our actual ratio not covering all the entire frequency band. So the actual ratio here, as we can see, starting from 4.6 until 6.1 and at 6.5, but from 6.6 until 7, that's mean this antenna has no circular polarization at this frequency band. So the next step or the next stage for this design, we have to enhance the actual ratio of this antenna to be fully used for circular polarization. One of the advantages of the helical antenna is provide high radiation efficiency. As we can see here from the result, the radiation efficiency that we have achieved is 97%. And the gain as well, it is high gain, which is 13.3 dBi, starting from 4.6 until 7.5. But usually for the antenna, wideband antenna, the gain increase when the frequency increase. I mean, the gain will be increased at the high frequency. But here, as we can see, is drop. So what we have to do here, we have to enhance the gain of the buzz antenna using AI or different method. For our design, we're using AI algorithm to enhance the gain of the proposed antenna. There is many type of AI algorithm that can be used to enhance the performance of antenna. Each of the algorithm has an advantage and a disadvantage. For example, genetic algorithm, particle swarm optimization, differential evaluation, and anti-colony optimization, biogeography-based optimization, gray wolf optimization, wind-driven optimization. This is all type of algorithm that you can use it to enhance the antenna performance. Uh, One of the advantage of the gray wolf optimization is easy to be used or easy and giving approximate result or value for the antenna. I mean to be enhanced. This is why we have choose gray wolf optimization GWO to enhance our antenna performance. So for those who are interested in the uh, AI to enhance the antenna, you may refer to the state of art and challenge paper, as I already referenced here, to uh, maybe have a look in this paper about the AI using the to enhance the antenna. So we have to continue here. So what is the gray wolf optimization? The or GWO algorithm. The basic idea of GW algorithm actually coming from how the wolf or the gray wolf family or group going for hunting. So as we can see here from hierarchy of GW, starting from the top to down, the leader of this group called Alpha because it's the best wolf in managing the pack for the group for hunting, and the stronger wolf in the family. Alpha, he is alpha as we can see in the position of the wolf alpha. Beta, which here is beta as we can see. Beta is the wolf who transfer the alpha's command to the peak, to the group, and send the feedback to alpha, which is the connecting between alpha and the wolf group. And the third type of wolf is delta. Here is delta. This group consists the hunters, the old wolf, or caretakers who submit to alpha, which means I mean by submit the information when they go for hunting. Here's the prey. Submit the information to beta and alpha. Omega, another type of wolf that submitting to another dominant wolves. So from here we can see the hierarchy of GW. There is no sigma. Sigma is one of the family group, but out of the hierarchy of GW, because sigma actually hunting alone or independence wolf. This why this from sometimes we call alpha male. This is from where coming the name of uh, sigma male. Sorry, sigma male character person. So here is the GW. This is how the wolf is working for hunting. So how can we use the GW algorithm to enhance our antenna? First, with the flowchart of the GWO, we start, and then and then the next step is initialize, which is set the parameter of the antenna, such as the size or the other type, or maybe the thickness or the substrate. So for our antenna, we choose N, P, and D. N means the number of tens. We have, as you can see here, we have 10. P, number of tens, it is 10, which is here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. B, the pitch angle, and D, the diameter. And then the next step is calculate the gain. Calculate the gain at each frequency and calculate the fitness as well. After we set the parameters N, B, and D, calculate the gain at each frequency and calculate the fitness. Fitness here will be shown in the next step. Determine social hierarchy. Identify the alpha, beta, and delta woof based on their fitness value, which means, as we can see here, the calculate gain, the calculate fitness, which means define in the next step which one is alpha, beta, and delta woof based on the hierarchy, social hierarchy. And next step, update woof position. For each woof, calculate new position using GW equations based on alpha, beta, and delta positions. This one, as we can see here, this is the position of the woofs, how they update each other to get the prey. And then the next step, check iteration. This is the most important part for those who is using AI to enhance the antenna performance. For example, imagine that you have a patch antenna and you want to optimize. In the CST, usually when we optimize the patch antenna, for example, we will key in the length and the width of the patch or the size of the antenna. 1 second, we will choose how many iteration, how many times, for example, 5 times, 10 times, 30 times. But by using the GW algorithm, it is different. In the GW algorithm, when we write the code, we will mention which parameter we have we need to optimize. As we can see, here is the N, B, and D. 1 second, we will choose what parameter of antenna we need to, our target. For example, for our antenna here, we trying to enhance the gain. In CST, we couldn't mention that. But in GWO, we have to mention our target gain. For example, 15 dBi as a maximum gain at the entire frequency band. Third thing, and very important, we can choose more than 500 or even 1000 as iteration to get the best value for the gain. So that makes the GWO as optimizer faster and more accurate compared to the CST. And then the next step is output. Determine the best design parameter N, B, and D from the alpha woof, which, as I mentioned here, alpha woof is the leader. So he will come, or the alpha woof will come out with a new value or updated value for N and B, and D. And then calculate and display the gain at each frequency using the base design parameters. If there is, the algorithm, if this is if yes, which is working. If not, we have to calculate to go to the calculate again, set again the design parameters, or maybe even add another type of parameter, maybe the size, maybe the thickness, maybe the substrate, and then the end. So here, the output, as I mentioned earlier, the wolf will come out with a new value for N, B, and D. As we can see here, here is the alpha wolf, come out with different value for N, B, and D. This value, as we can see, N number of 10, as I mentioned earlier, B is pitch angle, and D is the diameter. These values based
Sorry.
on the value.
Please conclude your presentation.
This is the last slide. Hello? Hello?
Okay, continue.
So this value is based on the equations using the CST. After we're using the GWO or AI, the alpha wolf come out with an updated value for the same parameters. So the 10 N, which is the number of 10s, changed to 10.5, B changed to 13.12 to 12.5, and diameter from 17.05 to 17.5. So here we have achieved our goal, which is enhance the gain. As we can see here from the simulated gain, for example, at 4.67 gigahertz, the simulated gain 12.2 to have been enhanced to 16.1. 7.17 gigahertz have been changed or enhanced from 9.94 to 16.23. 7.47 gigahertz have been changed or enhanced from 8.52 to 15.11, which means 6.59 dBi. This is the enhanced gain using AI. Thank you so much. And this is the end.
Thank you,
Thank you
Mr.
so much.
Mohammed Yousif Zeain, for your presentation.
You're welcome.
Maybe one question from the floor.
Okay.
Thank you very much. Interesting presentation. So please let me see the final slide. Yes, this one. So the parameter change is very small. However, antenna gain increases very
Much.
very much. So the maybe something antenna performance is changed. Current distribution or input impedance, what characteristics is changed?
Okay. So actually, in this antenna, we're using only 3 parameters, which is the number of 10, pitch angle, and the diameter. This is the number of 10. Can you hear me, Prof?
So maybe some antenna performance is changed.
Exactly, because that's correct.
Current distribution or something. You ensure.
Yes, Prof. Yeah, actually, in this design, we're focusing only on the gain. So how to enhance the gain of the antenna, and based on these 3 parameters. But we didn't study another type of, for example, maybe the efficiency change. We achieve here 97%. But when we enhance the gain, maybe the efficiency will be changed. So here only focusing on the gain.
So
Mm.
you have
One,
better check more antenna performance.
exactly.
Yes, current distribution may be more important.
Ah,
So
the
check,
current, mhm,
please explain later the
exactly,
difference of current distribution. Maybe.
exactly. Actually, we already here, if I can share with you one slide. Um, this one. This paper we already published a few months ago. Advanced helical antenna design for expand application using AI. Here, we're also using the algorithm, the same algorithm, but this result, the surface scan distribution of the proposed antenna based on the CST, not based on the AI. So the next stage, as you said, we have to focus on the surface contribution, how it will be changed, and the actual ratio as well. The actual ratio.
So make clear what
Yes,
antenna performance is changed so that improves the antenna gain.
correct.
So
But we
that
didn't
is
study that. We didn't
very
study that.
useful for antenna designer.
Exactly.
Okay, thank you.
You're welcome, bro.
Okay, thank you, Mr. Mohammed Yousif Zein.
Yeah.
Now, let's proceed to the next speaker. We welcome Miss Fitri Kurnia Sari from Universitas Trisakti, Jakarta, Indonesia, presenting design of a single port microwave sensor with a combination of an electric field coupled ALC resonator and an interdigital capacitor for characterizing solid and vegetable materials. Please welcome.
Okay, thank you. Can you hear my voice, Doctor?
Sorry, Yousif, can you
Can you hear my
Stop
voice?
sharing.
stop sharing?
Okay, sure,
Yes.
sure.
Okay, okay,
Okay.
okay. Okay.
Okay.
Okay.
We can see the slide.
Okay. Thank you.
Can you
Honestly,
can you full screen,
okay,
Doctor?
okay, okay. Is it okay?
Okay, now it's okay.
Okay. Okay. Honestly, it must be my student, yeah, present this presentation, but she was ill and she was in a hospital, so I take her place to present this presentation. Okay. In this session, I will present design of single port microsensor with a combination of an electric field couple, resonator, and interdigital capacitor for characterizing solid and vegetable materials. Okay, this is maybe I skip. So CV. Okay, this is the outline of our presentation. First, about the introduction, risk methodology, working principle of the proposed sensor, and development model of the proposed sensor, simulation result of proposed sensor, measurement and validation, and after that we continue to permittivity detection of non-materials, and after that we try to explore more detail about the permittivity detection of vegetable materials, and we compare our sensor with existing work, and we conclude. Okay, this is the introduction. As we know that the development of the communication system support Industry 4.0 through device integration enabled by IoT, with the microsensor being one of the key device involved. And the advance of the communication system support Industry 4.0 by enabling device integration through the Internet of Things with the microsensor, serving as one of the essential component. The microsensor are generally designed with a dual port. Usually, researchers propose microwave sensor using dual port with the band pass or maybe high pass filter, which bring a significant challenge, especially regarding to the complexity of the structure and the fabrication process that require high precision. And this research aimed to design the microsensor with a single port configuration that provides a simpler and more efficient structure. And the sensor is based on electric field couple, and we combine with the interdigital capacitor to enhance the electric field concentration. And this combination of the structure is designed to increase the concentration of electric field and minimize magnetic field in the sensing area. So this is the research methodology. We start from the literature review and determine the specification of the material for microwave sensor. And we do simulation and iteration with the M simulation. And after that, we try to combine the ELC and IDC in the resonance frequency 1 until gigahertz. And then after that, we fabricate the sensor and validate the performance in our laboratory. And this is the structure of our sensor, the combination between ELC and IDC. So if we can see in here, this is the ILC structure. And then for the sensing area, we use IDC structure to enhance the electric field of the microwave sensor. And this is the specification of the proposed sensor. Range frequency 1 until gigahertz for scattering parameter S11, below than minus 10 dB, and normal sensitivity is above than 0.5%, accuracy above than 90%, and for the frequency detection resolution is about 0.02 gigahertz. Okay, this is the working principle of the sensor. In our research, first we try to analyze and to determine the permittivity of known materials to obtain the polynomial equation. And after that, the polynomial equation that we got from known material, it can be used to determine or to predict the permittivity of the vegetables. For this research, we use 4 kind materials, vegetable materials that we can explain in the next slide. And this is the simulation of our sensor. You can see in here the sensor has a single band in the resonance frequency of 1.9 gigahertz. We fabricate and we simulate the sensor using FR4 substrate with permittivity of 4.3, substrate thickness 1.6, and tangent delta about 0.0265. Furthermore, when a material placed on the sensing area, the effective dielectric constant of the region increase depending on the permittivity of sample. This change result a shift in antenna resonance frequency toward the lower frequency. Okay, and this is the development model. So we also iterate the location of the sensing area. This is the model 1, this is the model 2, and the model 3. We also analyze based on the S11 and the resonance frequency. And we also analyze about the E-field concentration. So because we want to use this resonator as a microwave sensor, so we explore more detail about the electric field concentration. After we simulate the electric field, we can determine the potential location to place the sample. So the resonance frequency moves to the lower after we place the sample. The proposed microwave sensor is developed into the 3 different models to optimize its performance for permittivity sensing. Each model features a structure modification and to enhance resonance characteristic and improve the electric field concentration. So if we can see, this is the model 1. Okay, the electric field is very low. The E-field also still low concentration, but in the model 3, the electric field is more stronger than model 1 and model 2. So we can use the electric field in this resonator to detect permittivity of the sample. Okay, and based on the optimization using electromagnetic simulation, electric field analysis reveals that model 3 produces the strongest and the most localized field, up to 15 kilovolt per meter, offering superior sensitivity and precision in detecting the electric changes. Okay, this is we also simulate the sensor to detect permittivity in the range 1 until 10, and after that we also analyzed with a different tangent delta. And based on simulation, the return loss of S11 characteristic of the sensor demonstrate a distinct resonant frequency shift as the relative permittivity increases, with the resonant frequency decreasing from 1.984 GHz at ER1 and to 1.904 GHz at ER10. This monotonic and predictable shift highlight the sensor sensitivity to the dielectric environment at sensing region, confirming its suitability for microwave sensing, especially in distinguished material based on their permittivity. And we can see in here, in this figure, if we change the value of the tangent delta, okay, the S11 is downward. And the downward trend in the S11 curve as the tangent delta increases reflect the greater microwave energy absorption by lossy materials, resulting in a reduced reflection magnitude. This trend confirms that the sensor sensitivity to the electric loss variation, making it particularly applicable for detecting lossy substances such as biological tissue or food products. And this is the measurement and validation. We can see in here we use the portable VNA using Libre VNA at 1 until 6 GHz, and we can see this is the materials. This is the known materials. We use RO50, FF4, RO4003, the M10, and RO3006 with the permittivity range 1 until 9.8. And after that, we also use vegetables materials such as cucumber, tomato, potato, and carrot. And this is the response when we place the sample with non-permittivity. And after that, we can obtain the polynomial equation by a simple linear equation. So after we got the equation, we can predict we can predict the permittivity of cucumber, tomato, potato, and carrot. Okay. And the sensor is connected to the vector network analyzer through port 1 to measure the correlation coefficient. Then antenna is mounted on the standard PCB substrate. We use a FR4 substrate. And we can see in here that the material that we use to characterize is RO50, RO4003C, RO3006, FR4, and TM10. And for the vegetable sample, cucumber, tomato, potato, and carrot. And the measurement was conducted at ambient temperature 25 degrees Celsius within a frequency 1 until gigahertz and the sweep frequency 0.004 gigahertz. Okay. And all the sample has identical dimension 10 cross 10 millimeter with the thickness 1.58 millimeter. Okay. Based on the measurement, we can see in here, this is the comparison between the simulation and the measurement of our resonator. There was an error, but it's very small error. Okay, only 3.03%, which is relatively small and within acceptable limit for practical sensor implementation. And we can see in here, this is the okay, this is the characteristic based. This is the characteristic of the resonant frequency based on the material under test with non-permittivity, vacuum, RO50, RO4003, FR4, RO3006 and this is the polynomial equation that we use to determine the permittivity. And after that, we compare the permittivity from reference and calculation with this formula. And after that, we can compare the permittivity from datasheet and permittivity from calculation. You can see in here that the proposed sensor has a high accuracy in the range between 97 until 99% with the permittivity range 1 until 9.8. This is for non-permittivity. And after that, after we determine the polynomial equation with non-permittivity, we can predict the permittivity of the vegetables materials. As we can see in here, that the performance of the sensor in terms of S11 and frequency move to the lower while we place carrot, cucumber, tomato, and potato in the sensing area. So after that, we can calculate using this formula to determine the permittivity of the carrot, cucumber, tomato, and potato. Okay. And we also compare our research with the existing work. And based on this table, we can see that the main contribution of our research is first, we propose a single port configuration as a microsensor and combine IDC with ELC microsensor with high concentrated electric field. And we also propose the sensor to detect permittivity of solid and vegetables materials with high performance. For example, for FDR 0.054, and the sensing performance for accuracy is 98%, and for the normal sensitivity is about 0.69%. Okay, and the sensor also capability to detect vegetables and the solid materials. Okay, this is the conclusion. The proposed microsensor, which integrate an electric field resonator with interdigital capacitor structure, has proven to be an effective and accurate tool to detect permittivity of the solid sample and the vegetables materials. Operating at a resonant frequency 1.9 GHz and designed with a single port configuration, maintaining an S11 value below than -10 dB, the sensor ensures stable and efficient signal reflection that based on the polynomial fitting model developed from reference measurement on material with known permittivity in the range 1 until 9.8, enable precise estimation for unknown dielectric properties. In this research, we use vegetables materials for unknown permittivity samples. And the sensor achieve high accuracy is about 98.9% with the normalized sensitivity of 0.69%, and the frequency detection resolution is about 0.014 GHz, reflecting its high responsiveness and precision in detecting even small changes in the permittivity. So we also compare based on target simulation and the measurement. So based on this table, we can see from the measurement, the proposed sensor has passed the minimum criteria based on target and the simulation. Okay, this is the publication and output. We also published our research in progress in electromagnetic research, and another paper still under review in the sensing and imaging journal, also indexed by Scopus and WS. And this is my student, and this is me as a supervisor with Prof. Indra. And we also propose this research to achieve copyright from Ministry of Law in Indonesia. Okay, I think that's all from me. Thank you. I give it back to moderator.
Thank you, Doctor, for your presentation. Any question from the floor?
Thank you very much. Interesting presentation. So please
Okay,
show
no problem.
me your major data of vegetable, tomato, and something.
Okay. This is
Yes, this one. Potato. So I think they have a liquid material, and I think the permittivity may be complex value. So how you evaluate the conductivity included in this measurement?
okay. Thank you, Prof. In our research, in this research, we only calculate the real permittivity, because we use the polynomial equation based on the material with the non-permittivity. We don't observe more detail about the conductivity. So maybe in the future work, we will explore more detail about the conductivity. I agree with your question, because the materials, vegetables material is the we can also analyze the content of the water. So it's also has a effect with the permittivity, real and the imaginary permittivity. But in my student research, we only focus in the real permittivity. Maybe for the future, we will explore more detail about the imaginary permittivity and conductivity.
Yeah, that may be important. Only now you show the real part. In the future, you must show the imaginary part of permittivity. Thank you.
Okay, thank you, Pak.
Okay, maybe another question from the online session. The question is, are you satisfied with the difference between the measured and simulated value?
Yeah, based on the simulation and measurement, it's okay. I think the range error is about 3.03%. I think it's okay. Because if we design the microwave sensor, the most important, the resonant, the most important, if we design the microwave sensor, first, the location of sensing area is, we must determine the sensing location of when we put the sample. Is the most important. It's not like the antenna or we design the filter. We don't need the resonator as maybe reflection coefficient maybe below the -10 dB. It's okay if you simulate only got -5 dB, -6 dB. It's okay. The main important, if we put the sample, the resonant frequency move to the lower, so we can assume that the resonator can be used as a microwave sensor. I think that's all from me.
Okay, thank you, Doctor, for your presentation.
Okay.
Okay, now let us proceed with another presenter. Please welcome Dr. Farman Ali from Multimedia University, Malaysia. So Dr. Farman Ali will presenting the title of Future Directions for 6G UAV to Ground and Maritime Networks, Holographic MIMO and Distributed ISAC. Please welcome.
Hello. Bismillahirrahmanirrahim. Good afternoon. Thank you so much for the opportunity. The aim of this presentation to share the knowledge with each other and to learn from each other and what we are going in the field of technology and what we can learn from each other to improve further our interest and skills in the field of smart technologies. So the aim of this work is future direction for 6G UAV to ground and maritime communication. Why this topic is selected? Because as we know that the economy is from shipping the trades or goods from one country to another country through the maritime scenarios. So now the focus of the economy is increasing on the maritime ship communication. So how to communicate among ship, how to the movement of the ship organized. So we need to use some communication systems. So we have utilized low cost UAV to ship communication and UAV to ground communication. The second thing, we have used the word ISAC and holographic antenna. Why ISAC is considered here? ISAC is the intelligent sensing technology techniques. The main purpose of this, UAV will move and it will, by generative AI using, it will sense the environment and will take the decision by itself. And using what is the holographic MIMO use of this, the last one, is we know the traditional antenna in which we are focusing on the beam forming or the beam steering, how to maintain the beam among the ground user and the UAV. So here we will use the holographic, a new, this is not we have started work on this antenna, but it's the new form of antenna, which it will sense the whole area, and without any beam steering, beam forming, it will connect with the ground users. So this is my, oh, why it's not right? It is here. Okay, okay. Thank you. So this is my just short background. I'm connected with the three affiliations: Cordoba University, Pakistan; Nanjing University of Aeronautics and Astronautics, China; and Multimedia University, Malaysia. This is our first the issue cover page in IIT journals, which we have again this among 100 cover pages. This is our page, which is published in IIT journal. And the project, this is the list of our projects on which we are working currently. The projects I am currently working, sorry, it's a bit slow. The projects currently work with the Saudian projects, with Nanjing University of Aeronautics and Multimedia, and Cordoba University, Pakistan. So this is first I will show a detail about our ongoing research models, what we have done so far. So in the first work, we have worked on the UAV to ship communication. So how we can maintain the last probability among the UAV and the ship. So in the first era, we have modeled a simple mathematical model in which we have considered the UAV altitude, the shift wave, the state of the shift wave, and a distance, and some break points, decay points, and balance parameters. We have considered these things for our first project, how to maintain the UAV to ship communication in our first model. In our first model, we have used the AI model, dual deep convolution network model. We have utilized how to classify the last and then last links among the UAV and the ship. In our next work, we have considered the airframe of the UAV body with the ground communication links, how to maintain the communication link among the UAV and the ship, considering the factors of the airframe body of a UAV. So in this body, we have just added with the previous model and the second model, what we have added, we have adding the building up scenario and the value of the airframe shadowing factors, and taking the balance parameter, decay parameter, and balance parameter from our previous equation model, just with the addition of the building parameters and the airframe shadowing parameters. In our next model, what we have done so far, we cover in our previous equations, we focus on only the line of sight link among the UAV and the ship or UAV to ground. In this scenario, we have taken the maritime scenario, but here we have considered how to develop the channel model considering the wave shadowing. So while UAV is communicating with the ship in maritime scenario. So this is, and also we have considered the arc curvature as well, while communicating the UAV with the ship environment. So from this channel modeling, we have also secured recently a channel patent, which is published in 2024. The communication of UAV with the ship communication. Okay. Uh, Taking to these factors one by one. Next, in our next UAV to shape UAV to ground communication model, we concluded that how to utilize the UAV communication with the ground, taking the agriculture scenario. Mean if there's agriculture field, and how to collect the data from the agriculture and consider the the dry part, the insect-based part, the faulty parts, and the disease and the plants. So we have utilized this UAV communication for the agriculture scenario. Here, we have added a new words like the collaborative cloud computing. Why it is? Because to give a space for a high order of data taking from the agriculture field based on different classification. If it is insect based, if it is a dry soil and humidity and other parts of the. Secondly, our risk research model, we have taking this only this idea. The idea was the first for the agriculture communication, but here we have applied the same idea for the mountainous zones, in which where we can maintain the communication among the users in mountainous area. So these two works are the first work is currently published in the Transition Communication Journal. The next, in the next to maintain the same idea we have taken like the UAV to ground communication for the agriculture scenario, for the mountainous area scenario, but we have taken a bit shift with the applying a free space optics methodology. Why free space optics methodology? We came to know to maintain to decrease the latency among the communication links among the ground and UAV. So we have applied the free space optics technology, which has fast communication links, low latency, and low and high order of security rate. This work is currently under review in the Journal of Optical and Communication Technology elsewhere. So up till now, up till now, we have studied our ongoing projects on which we are working. But in future, what we are planning is I have discussed in our first slides that we are planning to for 6G communication to apply the holographic MIMO antenna with ISEC technology. So this is our future model, which we are planning to replace the traditional antenna design model. Like if it is shown from the, this is the visual video. We will, here what we will do, we will apply ISEC. ISEC will do what? ISEC will sense the ground environment, and MIMO will, what? Holographic MIMO will apply the beam steering equally on the same ground users. So there will be less chance of reducing the link or error or latency. So currently this is just a visual. This is our plan. So we need the help from the experts how to take this project more accurately in future. Similarly, we have also planned to apply the reconfigurable intelligent surface methodology with the UAV for the palm oil tree in the Malaysia. So what we are going to in this idea, we will take some ducts of the water drop, the elevation ducts, the free space ducts, and the operation ducts. So these ducts has some properties like the constructive interference and destructive interference. So what we will do here, we will apply our generative AI models. It will detect only those ducts of the water in the environment which can maintain the constructive interference links among the UAV in the ground. And if there's any faulty disease, so we can send data to our public safety communication stations. So as we know, currently for the holographic MIMO and ISEC technology, they have already has been approved by the standardization, the 3GPP, IITU, and IEEE. The 3GPP has already released the 19, and they are working on release 20. So we have also submitted our proposal for the release 20, which is expected to be published in 2027. And 3GPP have other, they have planned to apply to implement the 6G technology fully supportably from 2030. So our aim is to prepare our new research model for these scenarios. Thank you so much so far. So if you have any questions, so you're welcome. And also, we will be happy for the collaboration. If you have any are interested in our new research projects, so it will good for us. Thank you so much.
Thank you, Dr. Farman, for your presentation. Any questions from the floor?
Thank you very much. Interesting guidance for future work. So I'm not familiar with holographic MIMO antenna. So please explain more detail. Antenna structure and antenna performance.
Hello. Thank you so much. Actually, the holographic MIMO antenna is currently, this is the first time this work is started with the King Fahd University of Petroleum in Saudi Arabia, and I have done two to three meetings with them to work collaboratively on this. Basically, in holographic MIMO antenna, what we are doing, we will design a mattress of MIMO structures, and it will generate the signals, and these signals will holographically design a structure base like these chairs, everything with the help of ISAC. So all the ground parameters will be connected. Yeah, will be virtually designed with the UAV. So if he want to communicate with any other parameters, so that will be directly connected with them, with their person. Like in normal antenna, in normal models, what we are doing. This is if we have, this is a UAV, and this is a ground user. So in normal antenna, what we are doing, we have normal antenna like we have a side lobe. So what we are trying to do to connect this lobe with the ground user, and to maintain the reconfigurable this is surface. But for this is very difficult to maintain the ground user with the beam steering or the beam light. So what we are doing with the holographically, we will design the holographically like the mattress shape. This is the mattress shape, and mattress shape will design the links with the help of ISAC. It will detect the area here. So if I want to continue this main, so with the row and with the rows and with the columns, constructively it will work, and it will directly detect with this person. So with the here, it will maintain the communication link. If this person want to communicate here with another person, so again the signal will go, and the same phenomena with the rows and the column phenomena will be applied, and it will connect with the ground users. So this is a bit complex, but communication will become a very easier for us in future. I hope this will answer our question.
Okay, we have another question from the chat box. What are the challenges? What are the challenges to implement this?
The main challenge, everyone which we are know, is the money. To design this model, as I just said, so we need a huge amount of money. So we are applying for the projects. We need students to work on it and day and night. So this is our main challenge. So I hope we will get the money soon. So we'll
Okay, maybe that's all from Dr. Farman Ali. Thank you for your presentation. Now let's proceed to our last presenter, Dr. Norsiha Zainudin from Universiti Teknologi Malaysia, UTM, presenting evaluating SAR distribution of an ingestible NMHA in stomach tissue across MICS and ISM bands. Please welcome.
Kali lagi. Assalamualaikum and good afternoon to everyone. Okay, so today I would like to share our research findings about the evaluating specific absorption rate, which is SAR, distribution of an adjustable NMHA, normal mode helical antenna, in stomach tissue across the MICS and ISM bands. Okay, so my presentation will follow through these outlines. Kenapa? Okay. Okay. So we know that adjustable antennas are currently widely being used in the medical telemetry. So one of the example for the adjustable type antenna is the wireless capsule endoscopy, which is WCE. So the normal mode helical antenna offers a compact and omnidirectional antenna design that ideal for this adjustable type antenna application. So for the safe operation, it is crucial to evaluate the SAR distribution rate in the body. So the most commonly two operating bands that are widely used in the in-body communication is the MICS band, Medical Implant Communication Service band. Covers the lower frequency, which has the longer wavelength, and it has the deeper penetration, and it will cause the lower attenuation. So for the ISM band, it is covers at the more higher frequency, around the gigahertz frequency. So it has the shorter wavelength with the higher attenuation and stronger dielectric loss. So comparing this band is important to understand how the frequency dependence influence the absorption energy in the body, and to know how does it compliance with the regulatory standard. So the basic regulatory INIP safety limit is 1G SAR is below than 1.6 watt per kg, and for the 10 gram SAR is the below than 2 watt per kg. Okay, so the motivation behind this research is from these two key points, which is to ensure the SAR safety compliance, the essential for reliable safe operation for the implantable and adjustable operations. And number two, despite the extensive research on the animation performances in the body, such as the impedance, radiation patterns, and the gains, so the frequency dependent SAR characteristic have not systematically evaluated. So our aims in this research is to evaluate and compare the SAR distribution of the adjustable normal helical antenna embedded in the stomach tissue at two different frequency bands. And number two is to determine the permissible, which is the allowable input power levels for this kind of antenna design that complies with the INIP exposure limits. Okay. So our design will follow through this an animation design equation, which is it is animation in the human body where the design structure is normalized to the lambda G, which is the wavelength in the material. So our design, we design two types of antenna, which is A and B. So the antenna A is the NMHA in the stomach tissue at the lower frequency 402 megahertz, and the antenna B is at the higher frequency at the 2.45 gigahertz. Okay, this is our simulation model where we use the FECO simulator and we calculate it at the two different frequency bands. So the dielectric tissue is the stomach tissue, and this is the antenna structure from the equation previously. Okay, so this is the input impedance for those two antennas. So it is resonant at the targeted frequency, which is 402 megahertz and the 2.45 gigahertz. Okay, so this is the frequency dependent SAR analysis. We calculate the attenuation loss factor. So we can see that at the lower frequency, it has the longer wavelength and cause the deeper penetration with the lower attenuation. So at the higher frequency, we can see that the attenuation is higher. So higher attenuation here, which is it has the stronger dielectric losses. This is the permissible input power. So we can see that higher SAR at the higher frequency, so that lower excitation power is allowed for the SAR to meet the SAR limit following the INIP guidelines. Okay, so for the conclusion, we see that the higher SAR distribution is observed at the higher frequency due to the increase of the attenuation constant that leads to the greater dielectric loss. So which means that more localized energy absorption at a high frequency. So this effect arises from the frequency dependent behavior because of the attenuation loss in the biological tissue. So at a high frequency, a lower permissible input power is required to meet the SAR limit compared to the lower frequency. So the contribution of the research is to find out the importance of the accounting the frequency dependent tissues when designing in-body antenna devices to meet the regulatory limit. Okay, thank you for me.
Thank you, Dr. Norsiha, for your presentation. So, any question from the floor?
I want to know the efficiency of the results, because maybe we in the future you want to fabricate the antenna and then the phantom, right? So the efficiency of the current simulation results.
Okay, so in my presentation today, we are not sharing about the efficiency data. So for this type of antenna, for the small antenna, like the normal mode helical antenna, it's a small antenna. So we calculate the antenna efficiency from the impedance value. So in the future, yes, we would like to fabricate this antenna, then we have to calculate the efficiency. So nak kena tunjuk ke? So we have to calculate the efficiency based on the antenna impedance by the antenna impedance. So in the future, we will calculate that. Okay, thank you.
Okay, next question from the chat box. Why does you choose helical antenna instead of other type of antenna?
Okay, thank you for the question. So our research on the SAR distribution here is actually the extension from our previous research, which is the normal mode helical antenna types in the body, that we analyze the dependency of the body conductivity to the antenna impedance. So for that, for this kind of research, we specifically choose the wireless capsule endoscopy devices. So there are a lot of many antenna candidate that suits with that kind of the devices. So pneumomode helical antenna offers a compact size antenna that it is easily achieve the resonant condition in the body by the pneumomode helical antenna equation. We can let me show you. Okay, we can design many structure of the helical antenna. So at all this point, it is resonant at the frequency, at the operating frequency. So it is, we can say that it is easily resonant in the body condition. Okay, thank you.
Okay, so maybe last question from today. Maybe almost the same, the question. Why do you use this antenna for stomach tissues? What is the other antenna? What is the problem of the other antenna? Is the SAR value should be minimized?
Okay. In today, we share about the animation in stomach tissue. Previously, we also analyze the pneumomode helical antenna performances in fat tissue, which is the lower permittivity tissue, and it is showing similar good result with the stomach tissue. So this is only, we pick only one tissue that we want to compare the frequency dependence. So we pick only one tissue, one body tissue, which is stomach, but at different frequency, which is MICS band and the ISM band. Okay. So different type of antenna, it has a different value of SAR distribution. So it depends on the design itself. So that is why we have to know what is the permissible excitation power for that specific kind of the antenna type. So today we only discuss about the pneumomode helical antenna. So we realize that another type of antenna have different excitation power levels. Okay, that meet the SAR limit. Okay.
There is another two question. Can we use printed flexible helical antenna?
Printed helical antenna, we can replicate it as a middle line antenna. It is almost like the helical type, but it's printed on a board, on a flexible board. Dah. Okay. Oh.
Okay, last one. Have you done hardware implementation? Gain resonant frequency should be improved.
Replication. Okay. As I said previously, the SAR distribution is the extension research about the antenna, about the performances of the pneumomode helical antenna in the body. So I can share a little bit about our prototyping of the antenna. So previously we fabricate our helical antenna. So we measure the impedances. We compare with the simulation one in the specific body tissues. So in this case, in two different body tissues, which is stomach and also fat tissue. So slideshow. Tadi tak nampak lah. So we did measure the impedances and also the radiation pattern and the gain. But I'm not attaching the gain result in here. Uh,
Okay, maybe that's all for today. If you have any question regarding this matter, you can contact directly to Dr. Norsiha. Okay, thank you, Dr. Norsiha, for your presentation today. We have now reached the end of our program. We would like to invite Associate Professor Dr. Kamilia Kamardin, the Chair of IEEE AP Technical Meeting Steering Committee, to deliver the closing remarks.
Dia gerak jalan. Okay, Assalamualaikum warahmatullahi wabarakatuh and good afternoon. So thank you very much for everyone's participation as a speaker and as well as participants for today. We hope that this session today benefits the audience. Macam mana? Okay, so we hope that on behalf of AP Technical Meeting and RTPE Malaysia AP MTTE MC Joint Chapter, we hope that this event benefits everyone. So for everyone's attention, this year this will be the last AP Technical Meeting series hosted by us. The next one will be in February in UTM Melaka, but the exact date we will advise later. And we would like to also invite you to our conference, Malaysia Japan Workshop on Radio Technology MJWRT 2026, that will be held from 4 until 6 August 2026 in Kota Kinabalu, Sabah. So feel free to browse the website and you are invited to submit your papers for this conference. So without much further delay, I thank again everyone and we hope that this session is fruitful for everyone. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you, Doctor, for your thoughtful conclusion. Now, we would like to invite again Associate Prof. Dr. Kamilia Kamardin to present a token of appreciation to the research presenters. First, please welcome Dr. Farman Ali from MMU. Thank you and congrats to Dr. Farman Ali. Now we invite Dr. Norsiha. Okay, there's another from MMU, token from MMU. Okay, thank you and congratulations. Okay, On behalf of the organizing committee, we would like to extend our heartfelt appreciation to all distinguished speakers, participants, and collaborators for making APTM 5 2025 a success. Don't forget to fill in the attendance form for your e-certificate. Until we meet again at the next APTM series, thank you and have a wonderful day ahead. Assalamualaikum warahmatullahi wabarakatuh.